All right, folks. I'm glad you made it here, and I'm sorry that we got you up so early in the morning. I know some of you have traveled from far away, and I'm glad you made it in time. So anybody come here from across the Atlantic Ocean? Yeah, we have a couple of you there. What about the Pacific Ocean? All right. Now, it's a special moment for me because Linda Mutén and I, we were teaching here for 10 years between 2001 and 2011. And actually, how many of you came to one of those sessions? All right, repeat customers. All right. And actually, I taught the first course here 30 years ago, and it was on another program called ListComp, the program before Mplus. Anyway, it's good to be back, come back after 6 years, and we have a great team for you over these 3 days. I hope you're staying. How many of you are staying for all 3 days? Oh, wow, that's good. Yeah, there's a lot happening. We've been quite busy in the Mplus team over the last couple of years, producing this new book and producing version 8, which took it out of us. It was a big job, but we're happy with the result. And we're happy that so many people seem to be interested in coming. Actually, there were 303 people registered for, a total number of different people registered for these 3 days. Not everyone will show up, but at least that shows you the interest. Let's see. How many of you are actually using Mplus at this point already? Does anybody dare to raise their hand that didn't use Mplus? No. Okay. All right. Good, good. How many of you, though, feel uncomfortable raising your hands? We have to do that corny joke every time because it belongs with Sheldon Hall here. Anyway, when we were here, there used to be 2 screens, and now we have to get accustomed to 1 big screen. But it looks pretty good, and I hope you don't stand in its way. It's also a special moment for me today because I have a new partner with me here, Morten Schultzberg, and you're going to hear from him quite a lot today. We're going to split the day in half, pretty much. And he's an interesting guy. We have a lot of similarities, he and I. He started studying at the university a substantive topic, just like me. I started with sociology, and he started with psychology. Both of us found that the statistical part was the most interesting one. So both of us decided to get into statistics. I went into the Department of Statistics at Uppsala University in Sweden under the mentorship of Carl Jörskog. This guy went into the statistics department of Uppsala University, same place, same department. He's interested in research, and he's interested in teaching, and he's interested in software. All of those things that I'm interested in. And we have one more similarity, a genetic similarity. He happens to be my nephew. So, like I said, a very unique situation here today. So, this is the first time we teach together on a topic that we never taught on before. So, who knows how this is going to go? You're the guinea pigs, and we love to challenge ourselves, don't we?
Yeah, for sure.
Okay. Well, you'll hear more from him as we get moving. So, we're going to try to start, and we have a lot that we want to cover. That's why we start so early in the morning. And we'll have the usual format of 1.5 hour blocks, where the last 15 minutes are for questions and answers. So if you don't mind, if you can hold your questions to that part so we can move forward efficiently, just scribble down your questions on your handouts. Everybody should have a handout for today, and for tomorrow and Friday there'll be new handouts. And then we'll try to cover everything we want in these 4 parts of the day. I think we will have time for it. It's a challenging topic to cover. Some parts are quite straightforward, some are quite intense or deeper, but we're going to try to illustrate what we want to convey in both pictures, formulas, and examples. So it'll be a mixture, something for everybody. And the event is that we have this book on the left now, which you saw outside. There are 2 copies on the outside that you can take a look at. And we even have the user's guide version 8 printed now, finally. It got so big that the printers had problems with producing it, but now it's available from our website, as is this. So this book has 10 chapters, and we're going to work our way through most of them. We're going to sample very likely from the linear regression analysis, assuming that you know about that. We're going to get into mediation analysis and causal inference. That's what we also refer to as counterfactually defined indirect and direct effects. Categorical dependent variables is chapter 5. I mentioned that as a prerequisite for you, so we're not going to talk about that today. I hope you master that enough. Maybe in the future there will be a 2-day version of this book, where the first day would be introductory Mplus and categorical variable modeling. We're going to jump right into count and dependent variable modeling, count and censored, and mediation then with non-continuous variables, ending with Bayesian analysis and missing data. So you have this table of content shown on our website, the 500 pages book. We're now up to the 3rd printing, and lots of inputs and outputs on the website are posted, and many data sets as well. So you can take a look at the website and see if you want to reanalyze some data. So the morning is going to be spent on, in the first part, regression analysis of this kind. They count and censored after a warm-up example of linear regression. And then towards the rest of the late morning, we're going to get into mediation analysis. And we're going to make a distinction between classic and modern mediation analysis. And you're going to see that you need to learn about the modern version of it to understand what's happening in the literature. In the afternoon, we're probably going to continue with mediation analysis, actually using up the whole block 3 after lunch for mediation analysis, and save Bayesian analysis together with missing data for the last block. I think we can fit that in very nicely. So we're going to try to end at 4:45. This room has to be wrapped up by that time. So I have this outline then for our day. These different bullets. We're going to talk about some introductory topics, and then we're going to move into the guts of statistical modeling here, and onwards and upwards. So with that, I'm going to hand over to this gentleman.
All right. Thank you. Let's see if I can get used to Bengt's very large pointer. I will try. All right, so this will be a warm-up example to make sure that everyone is on the same kind of track. And even though it's in the prerequisites to have seen Mplus input before, I will try to give an example to give everyone a chance to come out of the vacation mode or whatever mode you might be in. So we're going to start with this example. We're actually going to look at this example several times today. So it's an example of a randomized field experiment in Baltimore, actually, elementary schools in Baltimore, and where they have this intervention trying to reduce the aggressive, disruptive behavior of students. So in this example, we have a treatment variable, which is an intervention to try to reduce the aggressive, disruptive behavior. We have the baseline aggression, so the aggression in grade 1, which we call AG1 for short, and the interaction between the treatment and the baseline aggression, TX AG1, and the outcome variable is the aggression in grade 5. Or disruptive aggressive behavior. I'm going to call it aggression for short. So the story here, why would we want to include the interaction here? This is a very basic example, but I will try to give you stories so you can kind of motivate what we're doing. And for example, it might be the case that people that have a high baseline aggression benefit more from the treatment than those who have very low baseline aggression. And that's kind of reasonable. If you don't have any aggression, then the treatment can't really reduce it, right? So it's reasonable that the baseline interacts with the treatment. All right, so how do we set this up then in Mplus? Oh, sorry, first let's look at some formulas for this. And this is just, these 3 lines is just a rearranging of terms here, really. The second and the first one, we're just acknowledging that Tx ag1 is simply the product of the 2 variables. So we say that Tx ag1 is simply the product of the treatment variable Tx and the baseline aggression ag1. And since we then have Tx in 2 places, we can take it out or factor it out and write Tx, and then with this whole thing in front of it, which we refer to as the moderator function. So you can think about it as the slope of the treatment effect, but in this case, the treatment effect is a function of your value of the baseline regression, right? So if beta 3 here is anything else than 0, then what value you have on your regression, your baseline regression, will affect how the treatment affects you. All right, so I think we'll go straight ahead for the input. So we'll see a lot of input files today, and I will talk through them in various levels of detail. The first one I'm going to cover in detail now, so just make sure that everyone is on the same track here. So the first thing you need to know about an input in Mplus is that it's not case sensitive. You can mix capital and small letters as you want to, but as a convention, the Mplus team has chosen to write all the Mplus syntax in capital letters, just to make it easier to read. So everything that is Mplus syntax is in capital letters, and everything that is user specified or names given by the user is small letters. And the second thing is that every line ends with a semicolon. And I think probably all of you know this, but I just want to make sure. So in this case, we start with the title command, and a command is always followed by a colon. So title and then colon. And this is just a name of this analysis. So this is the name you will be having on all the outputs that you get. So just to keep track of what you have if you have a lot of output files. And then we have the data command, in which we use the file option. And here you see file is a Mplus syntax, so it's in capital letters. Hopkins.dat is just the data file, which the user or the one who collected the data has given the name. So in this case, we say file equals hopkins.dat, and that means we're going to use a data file that is called hopkins.dat. And it's actually implied in this case that this file is in the same folder as the input, because we have not specified any path. But if it was not in the same folder as the input, we could simply specify the path. And then we come to the variable command, in which we can give, by the names option, we can give name to the columns of the data set. So we can give each variable in the data set a name. So in this case, the first column of the file hopkins.dat is the gender variable. And the second one is the design 11. And the third one is SCTA15, and so on. And then followed by that option, we can use the use variables option. And in this option, we choose what variables we want to use in the analysis. So we might have tons of variables in the data set, for example. We might only want to use a few in the analysis. The ones we want to use, we have to specify on the use variables list. So these can either be variables that are in the data file or new variables that we define in this input. So in this case, you see that ag5, ag1, tx, and tx ag1 is not on the names list, which means that we will have to define these variables. And besides choosing what variables to use, we can also choose what observations to use. So we might only want to use a subset of the sample. So in this case, we want to use the subset of the sample where gender equals 1, and this is males in this case, and where the design 11 variable is equal to 1, 2, 3, or 4. So this is a subset of the data, essentially. So we can do that in all sorts of various ways. And the second command is the define command, in which command we can rescale or transform variables or create functions of variables. And in this case, now we know that we will have to create these variables, right? Because they're not on the names list, and we're going to use them. So we define ag5 as SCTA15 divided by 10, and ag1 as SCTA11f divided by 10. So this is the regression variables in the original data set. We just rescale them by a factor of 10 here. And the reason why we do that is to keep the variance between 1 and 10, which is something that is usually recommended within Mplus to get the best numerical performances. And then we go on and create the tx variable, which is the treatment variable, according to the example. And we create that by the if-then statement. So we say if the design 11 variable is equal to 4, then the treatment variable should be equal to 1. So if it's equal to 4, then the treatment should be equal to 1. And if the design 11 is equal to 1, 2, or 3, then the treatment variable should be equal to 0. So apparently this design 11 variable is not exactly a treatment variable. We have to redefine it as a binary treatment variable. And then finally, we use the center option here to center aggression 1. And this is done to, and we use the grand mean for that. So you can read this line as center the variable ag1 with the grand mean. And the grand mean is opposed to the group mean, which you could use if you would have a 2-level model, for example. I'm not going to talk about that now. But why we do it in this case is to make the interaction interpretation easier. And then finally, we create the interaction variable, which is tx ag1, which is simply then the product of these two variables. And as you can see, we center ag1 before we create this interaction variable. And that's That's how we do it always. We never center the interaction variable. We center the variables before we create the interaction variable. And then we use in the analysis command, we specify the estimator. We can specify a lot of things here, but now we specify the estimator. And the default estimator is the maximum likelihood in Mplus. But in this case, we say MLR for maximum likelihood robust, which will give us robust standard error estimates. So it won't affect the point estimates, but the standard error estimates. So this is robust against some form of a non-normality and some forms of model misspecifications. And in this case, AG5 is a very skew variable, and that's what we do in this case. You can't see that, of course, but have to trust me, I guess. So we move on to the model command there, in which we can specify the regression that we want to look at. So in this case, we want to regress AG5 on the treatment variable, the baseline regression, and the interaction between these three. So AG1 on, regressed on. On is just short for regressed on. TX, AG1, and TX, AG1. And you see these things within parentheses. These are just labels for the parameters in this model, for the estimates, really. So what we say here is that the name of the slope of aggression 5 regressed on Tx is B1. We just call it B1. It's a name. So whenever you have something in parentheses after a variable in the independent variable in regression, it's just a name for the slope. So we give them the names, and why we have 3 different rows here is because you can only give one label per row in Mplus. But you see that this whole statement is ended by semicolons, so it will still be read as one regression by Mplus. And why do we name these slopes then? Well, in the model constraint, we're going to create functions of these parameters. So the model constraint can be used for a lot of things. We're actually going to use it for a lot more advanced things than this. But essentially what we want to do is we want to calculate the treatment effect for different values of the moderator. So the moderator here is the baseline regression, right? So we want to see what is the treatment effect if I have a high value of the baseline regression, if I have high baseline regression, what if I have the mean of the baseline regression, what if I have below the mean on the baseline regression. So what I create here is first I say I want to create 3 new parameters, mod low, mod 0, mod high. And as you can see here, we have essentially the moderator function that we talked about on the previous slide here. So we have beta 1 plus beta 3 times a value, and this value is minus 1.06, is 1 standard deviation of the aggression 1 variable. So it's 1 standard deviation below the mean of the baseline aggression variable. And then we have mod 0, which is the treatment effect when the baseline aggression is at 0. And 0 is the mean, right? Because we center this variable. So AG1 has the mean 0 now because it's a centered variable. So this is at the mean of the aggression 1 variable, what is the treatment effect then? And finally, 1 standard deviation above the mean. And then in addition to this, we can ask for outputs. And of course, there's a very rich default output for each analysis in Mplus, but you can always ask for more, kind of. There's a lot of information that you can get. So in this case, we ask for SAMStat, which is sample statistics. And we ask for patterns, which is missing data patterns. We ask for standardized results, which will give us the standardized results, and also R-square for this model, and residuals, which will give us information about residuals. And finally, we ask for plot type equals plot 3, which will give us all the available plots for this analysis. All right, so let's look at the output then. And just giving you a quick guide to the output, if you haven't seen one before, you have the first column with all the names of the what regression and what parameter you're looking at. So AG1 regressed on Tx. These are the slopes. You have the intercept, the residual variance, and also the 3 new parameters that we defined in the model constraint command on the input. And then the second column is the point estimate. And you have the standard error estimate, the estimated divided by the standard error, which would correspond to a Z-score or C-score if the normal assumptions are fulfilled, and then the p-value according to that Z-score. So as you can see here, the treatment effect and the baseline aggression effect on the aggression 5 is significant on the 5% level. We will use the 5% level if nothing else is stated, just to have some convention for that. But the interaction variable is not significant. So there seems to be no significant interaction effect here. However, if we look at the new additional parameters, we can see that the point estimate of the treatment effect changes with the value of the baseline regression, so with the value of the moderator here. When the moderator is low, you have minus 0.21. When it's at the mean of aggression, you have minus 0.28. And finally, at the high one standard deviation above the mean, you have minus 0.35. However, only the middle one is significant here, as you can see. And that's because it's not only the treatment effect that increases, also the standard error here. You see that the standard error is smallest at the mean of the moderator. Yes. All right, so let's look at, this will give us some kind of feeling for how the moderator affects the treatment effect, right? So how it moderates the effect. But this is only for 3 values. Of course, we could have specified a lot more values here. We could create, for a lot of different values of the moderator, we could create this or evaluate this moderator function. Another simpler way to do this is to use this syntax. So the same model, we give names to the slopes, but now in the model constraint, we use the loop option. So this is a nice feature to make this kind of analysis easier. So what we say here first is we want to create a variable that we call x. We want to loop that. So we want to create a vector of x values, really, from -1 to 1 with the increment 0.1. So from -1 to 1 with the increment 0.1, which will give us then 20 values, essentially. And then we say we want to plot something here. We want to plot effect, which is something that we will define. And effect in this case is then the moderator function at different values here. So x will take all the values from -1 to 1 with the increment 0.1 here. So we're just making a loop here, evaluating this instead of just 3 values as we did in the model constraint. We now do it at 20 values, and we will get a plot of this, and this plot that we see. And actually, we will get a smooth plot of this. So we don't see each point. We just see lines from this. So what we have here is the point estimates. So it's a line over these point estimates, and this is the standard, the confidence intervals, the 95% confidence intervals for these effects. So you can see here, we have the moderator on the x-axis here, so the baseline aggression on the x-axis, and the effect on the y-axis. So you can see as the aggression increases, the negative effect increases. So the negative effect, which means, which lowers than the aggression in grade 5, right? So if you have a high value of the baseline aggression, you benefit more from the treatment effect. But as we can see also, it's not significant for all values of the moderator. So for some values, the confidence interval covers 0 here. But for a part of the span of the baseline aggression, we have significant effect here. And I think, if you don't have anything to add, I think I will leave it to you then. To talk about censored variables.
That was very clear. Thank you. All right, folks. We have some people waiting for seats, and maybe you can find a seat. There are many empty seats, or unless you prefer to stand, we can take 2 minutes and let you be seated.
Blocking their view. Let's sit here, I think. Good idea. No, that's all right.
And while we're waiting, just behold these 3 pictures and have a lot of associations with them. Okay, let's start it up again then. So this choice of model for the dependent variable, and that is the regression model that you want to use, faces us all the time. You know, this choice is critical to get the right statistics going, to get the correct estimates. And throughout the day today, we're going to make decisions whether or not we want to go with categorical, whether or not we want to go with count or censored variables. And a couple of different considerations that you want to think about in that connection. So at the top here, we have 1, 2, 3, 4, 5 bars. So that could be a typical Likert or Likert scale, from strongly disagree to strongly agree. And really what the categorical variable model tries to describe is the probability of being in each of these histogram bars. In this case, the categorical variable is clearly ordinal. But we don't assume that it's continuous interval scale. It's not interval scale. That is, the step from this bar to this bar may not be the same as the step from this bar to that bar. So in this case, one thing you see in common between these three cases is that we have a high piling up at the lowest values, right? And the question is, what's the best way to deal with that? Is that a problem if we treat the variable as categorical, as ordinal? No, it's not. You have no assumption that is violated by having the highest bar to the left. These bars can jump around all over the place, and you still do correct categorical variable modeling. In contrast, if you looked at the bottom figure here, you have a high piling up at 0. That means that a standard linear model is totally inappropriate. Standard linear model is totally inappropriate because the assumption cannot hold 0 means for the residuals, for instance, for all points, particularly not the point at 0 here. Now, if you look at the count outcome, I'll get back to the censored in a while. The count outcome, how does that differ from the categorical? Well, it's still a discrete points here on the x-axis. But typical for count is that it answers the question, how many times did you, etc., do something in the last month or so? So it has to do, typically, as you see here, with very rare events. This is the bar for 0. Count 0 is often very high. But then it drops off very quickly. The probability drops off very quickly, down to 0. And we'll see an example of that later on. Now, certainly you could try to apply a categorical variable model to count data, but it would be an inefficient way of handling the modeling. This model has far fewer parameters than a categorical variable model. This has 1 or 2 parameters, whereas this one has at least 1, 2, 3, 4 parameters. So it's already twice as many parameters in this model as in this. So this is parsimonious, but it has to be a real count. Now in the censored case, like I said, it is really a continuous variable. This is supposed to illustrate a continuous variable, but one that has a strong floor effect. Alternative, you can talk about ceiling effects. And in my experience, if you have at least 25% or something like that at the 0, at the floor value, you really should abandon linear models, linear regression models, and go to something that acknowledges that you have a strong floor effect. And this is one way of acknowledging that. So categorical, count, and continuous censored. So we're going to try to decide which one we're going to work with. Now, 2 examples of this. So in this, of a distribution with a high floor effect, here we have economic stress, and the book in general draws on or uses a lot of examples from Hayes' 2013 mediation book, which I recommend. It's a very nice introduction to the topic. So he was kind enough to post data on this website, and they're used in our book. So here we have small business owners thought about withdrawing from the entrepreneurship due to economical stress. There's the average of 3 7-point items. And they were asked in these 3 items if in the next year they would avoid entrepreneurial positions, feel anxious about them, or less excited about them. So here, what would you choose? Which of these 3 models that we saw on the previous slide would you choose for these kinds of data? Well, it's not really categorical, right? We have an awful, if you do categorical, we have an awful lot of categories because there are many distinct values of the dependent variable given that we average 3 7-point items. So let's forget about categorical unless we want to categorize this variable, but that's losing information. What about counts? Now, it's not counts either, right? Doesn't have to do with counts at all. So here we should really try to do censored modeling of some kind. We should do modeling that avoids the linear regression assumption, takes into account, formulates a model for people at the floor effect, and specify a model that's correct for the tail out here. So censored modeling for that. What about example 2? How would you handle that? You don't have to have the answer in it, but you can think about it. You'll have the answer at the end of the day. So in this case, what about categorical? Well, let's see. What is the question? Is frequency of heavy drinking from the National Longitudinal Study of Youth? How often had you had 6 or more drinking on one occasion? So binge drinking on one occasion, one or more occasion during the last 30 days. Never, once, 2 or 3 times, 4 or 5 times, etc. 1, 2, 3, 4, 5, 6, 7 categories. So clearly, you could model this as a categorical dependent variable model, right? It would be ordinal, and there would be no violation of assumption because of this high floor effect. There's no assumption violated in ordered categorical, that is ordinal regression modeling. And when I say regression modeling, the reason why we wrote this book is that all the things we talk about in this book are directly applicable to much more general models like factor analysis models, growth models, or whatever. They're always consisting of building blocks that are regression analysis. Sometimes the X variable is latent, like a factor that influences an indicator, or a growth factor that influences the outcome at different time points. But the whole basic story goes back to how you do regression analysis. So that's why this is such a fundamental topic. Now, what about count modeling? Couldn't you do count modeling here? Well, there are 2 problems with count modeling. Count modeling, or the standard models for counts, don't have this feature of first going down and then coming up. The probability being high, going down, and then up again. That is not part of standard count modeling of the kind that we're going to talk about today. It could be count modeling if you consider a mixture of different kinds of people. So latent class analysis, where you have a class that's high here and a class that mostly does this behavior. But standard count modeling, this would not be appropriate for. And furthermore, you have this issue of you bunch together the counts 2 or 3 times, 4 or 5 times. That's not the original counts, right? It's categorized counts. And categorized counts you cannot count on following a count model assumptions. So I would go with ordinal variable regression here. Although we certainly will violate that ourselves, we're going to work with this example actually as a censored model, to continuous censored. So we take the step of assuming that this part of the distribution corresponds to continuous variable development. All right. Now, there are going to be some scary slides today, okay? They're going to have formulas on them. And judging from the 10 years that we taught here twice a year, some people don't like formulas at all and try to just listen to the words. But some formulas are accessible, believe me. We're going to walk you through these formulas. We try to simplify them as much as possible. And this is the slide that replaces your hour upon hour prerequisite study of chapter 5 in the book about categorical variable modeling. I'm going to give you 1 or maybe 2 minutes summary of that in case you already forgot what you read. So categorical variable modeling, I'm referring to binary outcome and ordinal outcomes, ordinals in the sense that we saw earlier. And we're going to work with a logistic model and also a probit model. So logistic, building on the logistic distribution, and probit, building on the normal distribution. In that chapter 5, we also deal with unordered categorical dependent variables, that nominal variables for which multinomial logistic regression is used. But I don't think that comes in today at all. It comes in other contexts, such as, well, let's not go there. So now we have to recognize, and here's the summary, 3 common ways to describe binary variable modeling with logistic regression. Because in different papers, in different books, you will see one of the three, and you think it's something different, but they're all the same. So these are all equivalent ways of expressing the model. The most basic way is to talk about the probability. And let's look at the picture first. Here you have a probability on the y-axis, probability of a certain binary outcome variable u, assuming the value 1 as opposed to 0, conditional on x, which in non-technical term means as a function of x. So you have x on the x-axis, and as x increases, the probability increases, but only up to 1, right? So we have to have a model where the probabilities are restricted to be between 0 and 1, otherwise it wouldn't make sense. So in this case, you can see then that if you think about slopes here, regression coefficients, it must be positive, right? For increasing x, the probability increases. So you could write here, I'm going to tell you to scribble a lot today. You can write beta 1 greater than 0. And beta 1, or beta 1 if you're British, is this term up here. So if you look at the probability here, it's a funny logistic expression. It can be written in this way in some journals and in this way, and it's just one and the same. You can play around with 8th grade algebra to show that these are the same. But what you want to focus on is where the action is. You have a beta 0, which is the intercept, and a beta 1, which is the slope multiplying x. E to the power of minus that, and plus 1, and 1 divided by that gives you the probability. So this expression makes sure that you're between 0 and 1. So here, this beta 1 is what you should scribble there. Beta 1 is greater than 0. We have a positive slope. So the higher the slope, the steeper the rise. The lower the slope, the flatter, the slower the rise in the probability. And the beta is an intercept parameter which shifts the curve sideways. Now you can write this in terms of logits, which is the same as log odds. Odds is then a probability of one thing divided by 1 minus that thing. And this expression within the parenthesis is the logit. It is the linear part of the model. So logit for the probability pi, this is the probability pi, we speak Greek a lot here, is this linear expression which sits here. I don't have a picture corresponding to that, but if you had a picture here in the between, there would be a line, a straight line that goes up as a function of x, as you see here. Now, we're going to talk very often about the third alternative, namely expressing the model in terms of a latent continuous response variable, which we put an asterisk on. The observed variable is u, the response variable, which is binary, and the latent continuous response variable is u star. And that's a function of beta 1x again, but plus a residual that we call delta sub I here, I being individual, varying across individuals. So now we bring in a residual, which we didn't have up here, right? So this is a variable with a regression and a residual, but where did the intercept go? Where did beta 0 go? Well, we work with the threshold concept instead. Instead of working with beta 0, we're going to work with tau, T-A-U, not T-A-O, which is the threshold here. So we imagine, and actually you can also write that the threshold is equal to minus beta 0 down here. Maybe we should move this podium so you can all see. But it's hooked up, so we can't move it too much. But anyway, so this is the u star axis here. It's a continuous variable, and we imagine that when that continuous variable increases large enough, you're going to be above the threshold and change your response from u equals 0 to u equals 1. So this formulation acknowledges that not everybody who answers u equals 1 are the same. They're ones that are just above the threshold and ones that are far above the threshold. So it sort of indicates that you could have measured this differently, perhaps with the Likert scale, perhaps even the continuous scale, but you didn't. And therefore you have a linear regression like this. Now, just to add to that, so we have a complete picture, this residual, for logistic regression, has a logistic density. But for probit regression, it has a normal density. And when I say density, it's the same as distribution. So logistic regression has a logistic distribution for this residual delta, and a probit regression has a normal distribution for that residual. And they have those residuals in the logistic and normal form have different variances. Typically in probit regression, well, first of all, you cannot identify the variance of this. The variance parameter is not the parameter of the model to be estimated. In probit regression, we fix it at 1. In logistic regression, it is implicitly fixed at, 2 pi divided by 3, something like that, something different, which makes the logistic and probit regression results come out on slightly different scales. All right, maybe that was more than 2 minutes, but that was a thumbnail sketch. That's all you need to know pretty much. So we're going to work, I think, with perhaps all 3 of these expressions as we go along today. But they're one and the same. It has to do with this probability model here. All right, so then we get into count dependent variables. And again, it may look a little unfamiliar, but you can do it. We're going to talk about the basic model here, Poisson. So you get to use all these wonderful terms now. And it talks about probabilities. You remember the picture that I showed you on the first slide? A high bar for 0 and then dropping off very rapidly. That's well described by something that looks very funny here. But if you look at it long enough, it'll tell you that you have one parameter, mu, that's a parameter, mu, and then the rest of it is either r, which is the number of times you did something, so that's the count itself, r here and r there, and then it's e to the power of, we're familiar with e, you know, e to the power of something. You can do that in your little hand calculator. So u varies from 0, 1, and up. Mu is the mean, or referred to as the rate. And this r exclamation point means r factorial. So as it says, it's 3 exclamation point is 1 times 2 times 3 equals 6. And we have to remember that r equals 0 gives the value 1. R equals 0 meaning not having done something in the last month. So that's a very important point. So when r equals 0, this becomes 1 down here. Mu to the power of r is then anything to the power of 0 is 1, right? Anything to the power of 0 is 1. So you end up with only e to the power of minus mu. E to the power of minus mu is the probability for having the count 0. Am I speaking too fast? Too slowly, I guess. All right, so now that's the probability, but now we want to do a regression. We want to relate this probability to x. So we use a linear regression, but it's linear only for the log of the rate. So log of mu is now linear, just like logit was linear. So statisticians, they make they focus on a parameter or a function of a parameter that makes the right-hand side linear. That is, it's not x to the power of 2, well, it could be, or it's not e to the power of x, rather, or something like that. And then, given that that's log of mu, if you take e to the power of that, it becomes mu, and on the right-hand side, we have e to the power of beta 1, which is the change in the rate mean of u for a unit change in x. So that's one way of interpreting the coefficient. But you could just go with sign and significance for beta 1 as to understand things. Now, the Poisson model can be extended to have a random intercept. And you write this then first as the linear equation that we had before, plus a residual, which can capture unobserved heterogeneity, just like regular linear regression. And that can be assumed to be normally distributed. And you can look alternatively at this, as we will do a couple of times today, as having a random intercept. So when you have a coefficient parameter, rather, that has a subscript I, that means it varies randomly, meaning that it varies across individuals. So this is not a fixed coefficient, it varies across individuals, just like in multi-level modeling. So, and then you describe that variation. The mean of that is beta 0, but then you also have a residual, a random part to it. If you express it like 6, the residual can be viewed as a continuous latent variable measured by the dependent variable log mu, where the variance is an additional parameter to be estimated. All right, that's one Poisson version. A more important Poisson version is the zero inflated Poisson. It tries to avoid the limitation of Poisson that assumes that the mean and the variance and the mean are the same. It's one parameter and it's both the mean and the variance. But very often in reality, you have variances much greater than the mean because of a high floor effect, preponderance of zeros. So take an example. In alcohol research, a common question format is how many times in the last 30 days did you drink 5 or more drinks on one occasion? The majority answered 0. Now we want to think about that. 2 reasons for the answer 0. Some subjects may be non-drinkers, and some subjects may be drinkers but have not engaged in heavy drinking during that period. So if you observe 0, it could be for 2 different reasons. We think of that as a mixture of 2 subpopulations or 2 latent classes. Those who don't engage in that because they don't drink, and those who happen to not binge drink but actually do drink. Now we don't know who's who by observing a 0, but by fancy statistical modeling we can tease it out. So a mixture is really something, has to do with latent classes, that is unobserved group membership. And we're going to try to, by analysis, figure out who's in which group. All right. Now if you accept that, then let's think of pi here as the probability of being in the 0 class, being a non-drinker, and then 1 minus pi, the complement, is the probability of being in a class that follows a Poisson model where 0 counts as well as positive counts can be observed, right? So 1 minus pi is the probability of being in a class that follows the regular Poisson model where 0 is allowed. So these are the drinkers, but they can have 0 binge drinking in the last 30 days. And then you write the probability as a mixture being then a sum of 2 parts, probability of being a non-drinker plus the probability of being a drinker but drinking 0, doing 0 binge drinking in the last 30 days. And here is the 0 count part that I mentioned before. You know, when the count R in that picture is 0, the Poisson model simplifies to this expression. So you have probability of being a drinker plus probability of not being a drinker and drinking, but not binge drinking in the last 30 days. So that kind of mixture is the hallmark of ZIP modeling, zero inflated modeling. And that kind of zero inflation, that is, that extra class of non-drinkers, that thinking comes back in several shapes and forms as we go on to other models. Now, in this ZIP model, you actually then have 2 parts to the model. Not only do you have the rate equation here, but you have the logit model. And here you see one of those 3 forms that I talk about. So this is the logistic regression here in the second alternative that I mentioned. So we logit for the probability is linear in X like this. That's the probability of being in the 0 class. And then you have the usual Poisson rate model here. And the interesting thing is that you don't have to have the same slope. Gamma 1, this is gamma 1, is not necessarily the same as beta 1. So a certain X variable can have different influence on the probability of being a non-drinker compared to how much they drink if they are a drinker. So that's very useful, very flexible modeling here. Whoops, I'm going to confuse these two. A very flexible modeling you can learn much more about your data by having 2 slopes from these 2 equations due to the zero inflated model. And the mean is then a little bit different than mu, is the mu times 1 minus pi. And you may want to circle this bullet, second to the last bullet here. If the logit gets large negative value, it implies that 0 probability of pi for being in 0 class, and the inflation part is not needed. That happens quite often in the examples that we see at Mplus support. Negative binomial model is another count model, very popular and perhaps better than even ZIP, zero inflated Poisson. It's expressed like this: linear regression plus a residual picking up unobserved heterogeneity. What do I mean by unobserved heterogeneity? Well, people with the same X values don't necessarily have the same rate or probability of the count outcomes. They differ. Even if they have the same x value, they differ because of unobserved variables that influence the log rate. And we put all of those unobserved in the residuals, just like we do in linear regression. Now here, negative binomial, that distribution is not normal. It's e to the power of epsilon has a gamma distribution. Gamma has to do with the chi-square distribution. So it's a little bit different. But as in the random intercept Poisson model, it accounts for unobserved heterogeneity. If we're using then the so-called neg-bin2 parameterization, there's a very good book by Hilby on negative binomial regression, a whole book devoted to that. Hilby 2011, you have the reference in the book that we're talking about today, our book. There's also a very good book by Scott Long from 2007, which I recommend. So it has a mean of mu, as does the Poisson model, and the variance is mu times this expression. So you have one more parameter here now. So you have two parameters, and that is the so-called dispersion parameter. The regular Poisson model is obtained when that dispersion parameter is 0, because then that term is 0. Variance becomes mu, the same as the mean, which was the limitation of the Poisson model. But having that alpha, particularly when it's greater than 0, the negative binomial gives much higher probability for low counts, just like zero inflated Poisson does, but without introducing a zero class. So it's not a mixture. Other count models treated in our book and in Hilby's book are zero inflated neg-bin. You can have a zero inflated neg-bin, binary count part like for zip. You can have a zero truncated count variable, zero probability for count equals 0. Certain applications call for that. And a hurdle model, which is what we will call two-part model today. We will not do a two-part count model, but we will do a two-part continuous model. And it's a binary model for being at 0 or not, combined with a zero truncated count model. That is, those are above 0, using then the zero truncated count part. And then you have varying exposure count models, which are dealt with in the book. Finally, how to compare these models? Well, all right, we're going to work in maximum likelihood settings now only. So in Mplus terms, we don't have the WLSMV, weighted least squares estimator. We don't have Bayes yet for counts, although that is in principle possible. We're going to work with Bayesian information criterion. Even though this says Bayes, it comes from maximum likelihood. It's called BIC. And it works with the log likelihood and the number of parameters. So the number of parameters is R here, not the count before, but it's a number of parameters, and it's the sample size. So you want to have a high likelihood, but you can get a high likelihood, which is a good fit to the data. You can get that trivially by just increasing the number of parameters. So you have to have a penalty for increasing the number of parameters. So that's why you have two terms balancing each other. So as it says here, a model with we want low BIC. And the way we're scaling things, low BIC is good. Some other software, high BIC is good. But for us, low BIC is good. Lower BIC is a better model in terms of balancing the fit of the model, which has to do with the log likelihood, and model parsimony, that is having few parameters R. And we multiply the R by the log of the sample size for theoretical reasons. But anyway, that's the penalty part of it. So BIC is going to be used to compare a series of models here. And with that, I'm handing over to the other speaker.
All right, so let's look at some examples of this ways to handle large piles of zero, essentially, count data. So if you look at this example, we have the dependent variable that is number of marital affairs reported in the last years. So it's the reported number of marital affairs. And we have the I'm assuming some measurement error. We're gonna. Okay. So we have the covariates having children, marital happiness, religiosity, and years married as things that might explain the number of marital affairs. And we have a sample size of 600 here. So we can look at this plot here where we have the different counts on the x-axis, and the dotted line or the dashed line here is the observed proportion of each count. So the first here is simply the number of individuals that had a 0 marital affairs count divided by 601. So 75% of the sample reported 0 marital affairs. And you can see there's a huge drop then to 1, where we have around, I guess, 10% or even below that. And the solid line here is the predicted probability from a Poisson model for the same count. So if we would fit a Poisson model to this data, the model would predict that we would have around 40% 0 marital affairs. So this plot kind of shows the problem of fitting a Poisson model to zero inflated data. You can think about it if you're used to regression, like fitting a linear regression to a nonlinear relation or something. We'll just fit the data bad, so it won't tell us much about it either. So how can we handle this? Well, we're going to start by actually doing a Poisson model, which we can assume from this fit plot here will not fit that well. But we will try that, and then we'll try other solutions. So to fit a Poisson model, which is a count regression really, the only thing you have to do is you have to specify that the outcome variable is not longer a continuous normal distributed variable. The outcome variable, the dependent variable, is a count. And this goes for anything. If the variable is not a continuous normal variable, then we have to specify for Mplus what it is, what it follows. So in this case, we say count equals n affairs. So the variable n affairs is a count-dependent variable. And actually, we could write within parentheses p, but that's the default Poisson. So you don't have to write, Mplus is known for the default, so we could just, it's an implicit p within parentheses. But we're going to change that in the following input. So I just wanted to show you that there is an implicit p here. So that's kind of everything you have to do to do count regression. And then in the model command, we simply then say n affairs on some variables, and you don't have to say anything about that this is a count regression now, because you have specified that this is a count variable. And we have the covariates here, kids dash years married 6. What is that? Well, a dash implies a list. And to make sense of this list, we have to go back to the use variables option. So if we look at the use variables option, we see they have the outcome variable n affairs, and then we have kids, and then a lot of covariates up until years married 6. So if we say kids dash years married 6, that will imply all the variables between these two. So essentially, this means regress n affairs with a count regression on all the covariates we have on the use variables list. So it's just a short way of writing that. And then we can ask for, we can specify the estimator. Like Bengt said, we will use ML here, and for plots. And if you wanted to have a random intercept for this model, as Bengt talked about, which you can want to have for several reasons, it might make sense, but also to introduce kind of an error term, because there is no error term to the Poisson model by default, you could just add a factor. So you say f by n affairs in addition to the count regression. So you add a factor behind n affairs, and the only new parameter you will have is the residual variance of that one. So the residual variance. All right, so that was the Poisson model, but as we could see from the plot, it didn't seem to fit the data well. So how can we try to do something about this? So the first thing we'll try out is the negative binomial model. And as Bengt just said, what we do essentially is that we add a dispersion parameter, allowing for the Poisson model essentially to have different mean and variance, right? So if this dispersion parameter is equal to 0, like Bengt said, we will have the Poisson model. But if it's larger than 0, then the negative binomial model will shift some probability to the lower counts. And if we go back to the plot here, that's exactly what we want. We want to shift some of this probability to the lower count here, right? We want to move some probability mass. So we can do that just by saying NB, negative binomial within parentheses. That will add this dispersion parameter. We could also add inflation here, like Bengt said. We could not, maybe it's not enough to just shift some probability. Maybe we also have to add this mixture at 0. Think about the 0 as two different kinds of 0. The ones who never drink and the ones who actually drink but didn't drink during this 30 days, last 30 days. And that can easily be done by adding an I, negative binomial inflated. So what we'll have to add then is the model for the probability of being in this never drinking class. So the probability of being in the 0 class here. So that will be, the first is the count regression, and then we have to specify this regression. So you have this number or hashtag, depending on what generation you are in, 1 referring to the latent class of being at the lowest value, being a never drinker, sorry, 0 drinker. And you have, we will use the same model here now for simplicity. But you could in principle have other variables in this model. And of course, you could also, like Bengt said, add the inflation to the Poisson model. If you think that it would be enough to just model the inflation, to model the zero as a mixture, you could add an I after P, so Poisson inflated. All right, so now we have many models, but I will try to summarize in a bit. But let's just look at the outputs you get from a count model. There's some outputs that you get by default when you do a count model that you don't get from usual regressions. So this table is something that you get, and this is a really nice summary. So what you see here is the count proportion of 0, minimum, and maximum values. So you should read this as the dependent count variable n affairs has a proportion of 0, 75, or 75% of the sample reported 0, marital affairs in this case. The lowest value was 0, which is reasonable for a count variable, and the highest value was 12. So this kind of gives you an idea if this is reasonable to model as a count model. If you only have from 0 to 3, then it might be good with an ordinal variable, ordinal model. And if you have 200 here, then it might be able to use a continuous model. So in addition to this, you get the log likelihood, you get parameter estimates, standard errors, the Z scores, and the p-values. You can also get plots of observed proportion estimated probabilities, and that's exactly what we saw. You can get them in two ways: not conditioning on any covariates, so that's just averaging over all individuals. That's exactly what we saw. We could also condition on covariates, so then you could choose for what values of different covariates you want to see this plot. So this is this plot for the negative binomial model. So we have the observed proportion and the estimated probability from the negative binomial model. And you can see, you should compare this to slide 25, then the previous plot. I'm not going to flip back, but the previous plot, the similar plot. You can see that the model is much more able to account for this massive amount of zeros, right? So just by moving some probability mass to 0, just by allowing for dispersion, difference between the mean and the variance in the Poisson model, we can capture this a lot better. So you only have to change one letter in the syntax to get this much better fit. Seems worth it, I guess. And this is the output. So we have two outputs here, actually. So this is the output for the Poisson regression, and this is for the negative binomial one. So even though we know now that from the plot we saw that the negative binomial probably fits the data best, let's just look at it. We see that we have, for example, very happy. If you're very happy in your relationship, in your marriage, that decreases the count. And it's a significant effect because the Z score is larger than 2 or larger than 1.96 absolute values. And we can see here that everything is significant here, and you have very small standard errors if you compare it to these ones where not everyone is significant and you have larger standard errors. And this is something that you see commonly, even if the negative binomial model fits better. Even if you have a significant dispersion parameter, you usually see this. So a good idea is to try the negative binomial model in any case and see if the dispersion parameter is significant, and compare the plots of the fitted and the estimated probabilities. So we can see here that they agree on the very happy variable. It's still significant here, and the estimate is very similar, but some other variables are very off and go from significant to non-significant. For example, years married 3 is significant for the Poisson model, but not for the negative binomial model. And in this case, we would probably trust the negative binomial model more, given the fit. And then we have the negative binomial inflated, or the zero-inflated negative binomial model, where we have two regressions, but in the same model now. So we have first the count equation, but then we have the inflation equation, right? Because now we model the probability of being in the never-drinker class as well. And this is interesting. If we look at very happy again, very happy in your marriage, you see that it has a negative effect on the count and a positive effect on the inflation equation. So different signs there. Does that make sense if you think about it for a while? Well, actually it does, because what we model here is we see here is the negative effect. So if you're very happy, that lowers your count, but it increases the probability of being in the 0 class, right? So that's reasonable. If you're very happy, that increases your probability of never having any marital affairs, and it also lowers your count of marital affairs in general. So it has the same kind of effect, but with different signs here, because we're modeling different things. One, we model the count, and the second, we model the probability of being a never marital affair, or whatever however you say that. And as you can see here, the dispersion parameter, sorry, I should say that in the previous plot here, the dispersion parameter was in the heading. Sorry, I should have mentioned that. And it's a significant dispersion parameter for the negative binomial one. It couldn't fit in the table here, so it's a significant dispersion parameter. So the mean and the variance is not the same here. So it's not reasonable to assume the Poisson model, which we could expect given how much better it fitted the data. But I just want to say here that even when we add this inflation equation modeling the 0s mixtures, the dispersion parameter is still significant. So the SIP model here kind of suggests that it's not enough to model the zeros as a mixture. You also have to shift some probability for the count equation to the lower counts. So you kind of need to, in this case, take into account in both ways. And then, of course, you can compare these models. And we're going to use now, since they have different number of parameters, we have to kind of focus on the BIC rather than the log likelihood to take that into account, like Bengt showed you. And as you can see, and now again, the lowest BIC is the best, so to speak. And as you can see, the negative binomial one has the lowest BIC, right? So, and followed by the zero-inflated negative binomial one, which we just saw, and the two-part hurdle, which we didn't look at the output for, or the input, actually. But it's kind of similar where we modeled as two parts. So we might want to stick to the negative binomial one here, but we could actually, maybe from substantive reasoning, stay with the zero-inflated negative binomial model or the two-part model, because we get more information, right? As you can see, we get more information about the processes. We get kind of a more elaborated story about this, which might be very useful. And of course, the choice of which model you use should be based on some kind of substantive theoretical reasoning, right? Does it make sense to model the zero as a mixture? Well, and if it doesn't, then maybe we should stick with the negative binomial. But if it makes sense and it gives us a lot of insights, and we have this significant dispersion parameter still, then maybe we should stick with the inflated model. And with that, I think, if you don't have anything to add, Bengt, I think you're up again.
Thank you. And just a little, I'll stand on this side just to vary things. Also because I'm left-handed and he's right-handed. There's a dissimilarity there. So if you look at this, the inflated models here, they have a lot more parameters than the non-inflated. And why? Well, because we regress the inflation probability or the latent class variable onto x variables, and there are many x variables. So the whole extra set of x variable coefficients related to the inflation that comes in here. Now, I actually played around with these data the other day, just I had nothing to do. So, and it turns out if you don't have your inflation part model, the probability of being in the zero class or not, it doesn't have to be regressed on the x variables. It can be just a constant. It doesn't have to vary with x's if you don't want to. And then, in fact, I think I beat most of these BICs. I came down very low here. But of course, BIC is not everything in life. For us it is, but it's then a matter of, well, Morten showed you that many of the inflation regression coefficients were significant. So it's sort of, you miss the story of significant influences on the being in the zero class if you do what I did, namely get rid of them. But I just want to mention that you don't have to have x's for the inflation part. This comes into play also in growth modeling, where you don't have to have a growth model for the inflation part. Anyway, so here's where we are now. If you're lost, we went through this, and now we're here. And we're going to end here before the first break. We're going to go through this and then do the rest afterwards. So now, let's get back to this censored variable situation. This was the economic stress data, and this was the heavy drinking data, right? And when we agreed that we should use a continuous censored variable model for the economic stress example, and we said we could also perhaps play around with it for the heavy drinking example, and treating this as a continuous development here, although we probably perhaps should take the categorical approach for these data. When it comes to choosing between linear regression and censored regression, it's critical to know, and I always look for this in the summary statistics that come out of Mplus, how many people are at the lowest value. You know, you get a special output information about that. 30% here, 50%, 59% here. And even here, you know, with 30%, that's above my rule of thumb threshold, 0.25. So even in that case, should you get into seriously try to model this part of the distribution, so censored variable modeling. So we have a lot of choices there too, just like within accounts. So now we're in the area of censored modeling, and we can have censored normal modeling, also called Tobit, after Tobin, and censored inflated, so that the inflation comes in here with the zero class, or sample selection modeling, which is also called Heckman modeling, after Jim Heckman in Chicago, or two-part modeling, which exists for count outcomes, but now we're going to talk about it for continuous outcomes. So here's a picture which takes a little while to digest, but we can do it. We start with a picture, top left here. What's on the x-axis? Well, it's a predictor or a covariate x. What's on the y-axis? Well, it's the continuous variable y. And you note that if you tilt your head to the left, we're going to do that a lot today, you see the distribution of y here. It has that tail and then a spike here. And the people are the dots here. The observations are the dots. Several people for low x values have y equals 0. They're these guys. And then for a little higher x values, they start increasing their y value. So start with reading the dots. Now, if you do a correct analysis, you will have this slope, Tobit analysis. But if you take a regular regression analysis, as it's often called OLS, ordinary least squares, you will get this kind of slope, this kind of line, that is you not taking the censoring into account and doing OLS underestimates the slope on x. So underestimating the slope of x, if you ignore the censoring, is a typical outcome. So what censored normal or Tobit regression tries to do is to figure out where these guys on the y equals 0 line here of x, where they should be. And we try to stretch them out like this. We place them out in this tail of the distribution. You know, these guys, if you tilt your head to the left again, they create a tail. We stretch them out down here. And we do that, of course, by statistical magic, as usual. How can you tell where they are? I mean, these people, how do you know how far down on the tail they are? Well, you know something, x. You estimate the regression coefficient for x, and you see that for low x values then, the lower the x value, the higher the probability that they're far down the tail. That's how it works. And of course, then you can see that it relies heavily on the distributional assumption for this, the distributional assumption for the tail. We're going to work with the normal because that's the standard model here. So you see also that I changed from y to y star here for the dependent variable. And y star is then the continuous latent response variable, just like u star was earlier for binary outcome. So we have a linear regression for y star. It has an intercept, slope, and a residual. And we're going to say that the observed value, y is the observed variable, has the value 0 for if y star is less than or equal to 0. And it's observed identical to y star if y star is greater than 0. So that's the censoring. Everybody who has a value less than 0, all of these people get smashed into one pile of people in this not distinguished between. So that's what this says. That's the Tobit model. And it has two parts then. You have a binary part for modeling the probability of y greater than 0 or not. And with normality assumption, that's 1 minus the probability of being below that point. This is the standard Stat 101. Phi is a normal distribution function. If you want the probability of being below, it's the value itself, 0, minus the mean, which is this part. This is the mean. divided by the standard deviation. All of this given x. So value minus the mean divided by standard deviation, that is the normal distribution function argument. So that's the probability of being below 0, and 1 minus that's the probability of being above. And due to the symmetry of the phi function, we just change the sign of this to turn it into getting rid of the 1 minus, and then having plus beta 0 plus beta 1 divided by this. Anyway, that's how it works. Continuous positive part, expectation here means, it says that it's the mean in the population for y. For those people who are above 0, these people, what's the mean? What's the mean function? Well, it's the irregular regression coefficients here, beta 0 plus beta 1x, but then plus a term, which is the normal density. That's a normal distribution, lowercase phi, and this is the normal distribution function again. This is a nonlinear term which captures the shape of this. Now, we estimate both of these parts, and the limitation of this model is then clear here, that this beta here for the probability is the same as this beta for the continuous positive outcomes. We would prefer to have them different, but in this first model, they're one and the same. So we're going to go to sensory inflated regression, where we're going to end up with one equation with gamma 1 and one equation with beta 1. We're going to make those slopes different, just like we did for zero inflated Poisson to make that more flexible. So once again, we're going to have a latent class that we call class 0, subjects for whom only y equals 0 is observed, and a class 1, subjects following a censored normal Tobit model, as on slide 37. So then we have a logistic regression that describes the probability of being in class 0, a linear logit model as usual, standard logistic regression, and for subjects in class 1, we have the usual censored normal for y star here. And once again, there are two ways y equals 0 is observed. It's a mixture at 0, just like for the count. So it's very similar to count inflation. So inflation, once again, means that you have a class at 0 and a class that can be above 0. And it helps modeling the outcome in a more flexible way. Two different slopes. Sample selection Heckman modeling is related to this, but slightly different. So the y star equation looks very much the same. But in this case, the latent response variable is observed as y star, just like for Tobit, but remains latent, that is missing if u equals 0. So it's missing in this case. This was developed by Jim Heckman and others for wages of female labor participants. If a female was in the labor force, they would have an observed wage, y equals y star. But if they weren't working, then the wage is not 0, but it's missing. We don't have an observation for what the wage could have been if they got into the labor force. In this case, Heckman works with a probit regression for U star. So the residual delta is normal. And we have the usual threshold formulation for probit. Instead of an intercept gamma 0, it's a threshold tau, measuring whether or not U star is above tau, the thresholds. And the key feature is that the residuals epsilon and delta, what are they? They're sitting here, epsilon and delta. They are assumed to be correlated and have a bivariate normal distribution with the usual probit standardization. So they are correlated potentially. And now you never observe both of these, U stars and Y stars. You only observe part of the picture, that is, when a woman is working, you observe Y star. So two-part regression then as a final version, censoring from below at 0 and using probit regression. The two-part model is probit for pi, and then we have a special model for the log of the outcome for those who are not at 0. So this line, vertical line here, is given that we are considering those with u equals 1 in the u equals 1 class. So we have a linear regression for that. And you can have a logistic regression if you want to, instead of probe regression. The interesting part here is a maximum likely estimation of the two-part model gives the same estimate as if the binary and continuous parts were estimated separately. But in this case, we have bivariate normal residuals, and they can be correlated. But the point here is that the correlation does not enter into the likelihood and is not estimated. And that is a strength of this modeling. You don't have to, for Heckman modeling, you have to assume bivariate normality for epsilon and delta, those residuals. And that model has been severely criticized by statisticians for that reason. But in two-part regression, you don't have that feature. So comparing them finally then, censored inflated, Heckman, and two-part. Like the censored inflated and Heckman models, the two-part model has a different regression equations for the two parts. So gamma 1 and beta 1. It was the Tobit model, the censored normal model, that only had one slope. But we have two slopes for all of these three models. But unlike the censored inflated model, the two-part model does not have a mixture at 0. And nor does Heckman. So the mixture is only for the censored inflated. So two-part modeling and Heckman modeling does not involve mixture modeling. And unlike the Heckman model, a two-part model does not estimate the residual correlation between the two parts. And this was stressed by Noah Duan, who was at the RAND Corporation in the 80s in Santa Monica, California, is now at Columbia, pointed to two advantages of the two-part model over Heckman. He worked with medical care expenses, which they studied a lot at the RAND Corporation. And he thought the two-part model was preferable to Heckman because a censoring point of 0 expense does not represent missing data, but rather a real observed value. So he didn't buy into Heckman's missing data thinking. And the bivariate normality assumption for the residuals is not needed. So two-part modeling is quite useful, and it also comes back in growth modeling, where it's very useful as well. Okay, and with that, I think it's back to the other speaker.
Yeah. All right. So now we're going to look at heavy drinking. So what we have here is a dependent variable that looks like this. So it's the frequency of heavy drinking measured by the question, how often did you have 6 or more drinks at one occasion during the last 30 days? It's the same variable that Bengt talked about before. And we see that we have this huge pile here of zeros in this case. And what we have to kind of model this is some covariates. We have the gender, the ethnicity, early onset of regular drinking, family history of problem drinking, and high school dropout. So we have some covariates to try to figure out why it looks like it does. So we're going to do this in two ways now. And this is very, very similar to the negative binomial model and the negative binomial inflated model, right? In that case, we started with the Poisson model, which was the default. In this case, the default is just a normal, so we don't have to do that. I think everyone knows how to do a usual linear regression. So how do we start? By shifting some probability or doing the censored normal or the Tobit model, which is essentially shifting probability to the lowest point, to the cut point or the floor point. We do that by using the censored. Like I said, if the variable is not continuous normal, the dependent variable, the outcome variable is not continuous normal, we have to specify what it is. Before we say it was a count variable, now we say it's a censored variable. So we say censored equals HD, which is heavy drinking. And then a B within parentheses, and this B is now from below, censored from below. We can have censoring from above and below. So this is B for below. And that's everything we have to do. And then we just specify our regression like we would. And the second alternative is then to add the inflation equation. So add the mixture at 0. So just like with the negative binomial, it might not be enough to shift some probability to the lower point. We might also have to model the inflation to add a mixture at 0. So in this case, it makes sense, with the heavy drinking example. There might be people that never drink, And there might be people that usually drink sometimes, but they just did it 0 times for this month. And the way to do that is simply by adding an I, so censored from below with inflation. And again, when we add the inflation, then we have to add the corresponding model for that. So we have to model the probability of being in the never drinker class. So we do that just in the same way. So it's very, very similar. All right, so now we're going to look at the data 2 part. So this was 2 models, two ways to do it. We have the sensor and the sensor inflated. Now we're going to talk about the 2-part data command, which we use to create data for the 2-part model and the Heckman model that Bengt just talked about. So the data 2-part command is a convenient way to create this variable, because what we essentially do is that we create one binary and one continuous variable from this original continuous variable. And we do this with the following rules. So if the value of the original variable is missing, if you have a missing value on the outcome variable, then both the binary and the new continuous variable will be missing, because the binary variable is whether or not you're a drinker, if you have 0 or not, and the second one is how much did you drink. And if you have a missing value, then we don't know if you're a drinker or not, and we don't know how much you're drinking. However, if the original variable is greater than the cut point, and the cut point in this case is 0, we can specify the cut point, but in this case it makes sense to have it at 0, and that's where we have the floor effect. If it's greater than the cut point, then the new binary variable will be 1, you are a drinker, and the continuous variable will be the logarithm of the original value. So we will take the logarithm of your amount of drinking, so to speak, and that is to better fit the normal assumption of that. I don't know if we... And that's essentially what we're trying to do, is make this part look more normal. So in this case, I don't know if it makes perfect sense to use the logarithm. We will use it. It's the default. And we will look at other examples where we override this default and have no transformation. But essentially, if the other part here, the cut-off part, so the positive part, if it looks like a normal variable, then that's fine. But that's what we want it to look like. We want it to look like a normal, and usually we have this long tail that we want to pull in by using the logarithm. So if it's greater than the cut point, then the binary variable is 1, and your positive value is the logarithm of your original value, so the logarithm of the amount of drinking. And if the original variable is less than or equal to the cut point, so if it's 0 in this case, then the new binary variable will be 0. You're not above the threshold, and the continuous variable will just be a missing value. You don't have an observed value for the amount of drinking. So as Bengt said, we can analyze this data in 2 ways. This is how we create the 2-part data. The 2-part data we can analyze with a Heckman model or a selection model, or we can model it with a 2-part model. And like Bengt said, the main difference is essentially what we assume about the correlation, or if we model the residual correlation explicit or not. So that's the main difference. But we're going to look at the data 2-part command to start with, which is the same for both of these models. And what we do there is we state the data 2-part colon for a command, and then we say names equal HD. So the variable that we want to create a binary and a continuous variable from has the name HD for heavy drinking. And then what we want to call the binary part, so we want to call the binary part U here. So U will be the variable that codes for if you have a value larger than 0 or not. And then the continuous part, we will call that part positive. So positive and U are names. And remember now that positive is the logarithm of the original value. So if you want to write that or scribble, like Bengt says, you can just scribble, this is the logarithm of the original value here, which you can override, and we will do that in another example. But then they differ a bit in the analysis command. I will get back to that. I think we'll start by looking at the model command. And of course now, since you have a binary outcome variable, one part is binary, you have to specify that this part is binary. Like I said, if you have a dependent variable that is not normal continuous, you have to specify what type of variable it is. If it's a count, if it's a sensor, in this case, if it's a categorical. So you have to specify that categorical is, U is a categorical variable, and also mention these variables on the use variables list. But then we move on to the model command, and they have similar regression first. We have positive and U regressed on the covariates. Both have that. But then in the Heckman model, to get this explicit estimation of the correlation between those two, the covariance, we have to add a factor. So we put a factor indicated by U and positive. And the default in Mplus is to fix the loading of the first factor. So the loading of the binary outcome variable here will be fixed to 1. And the positive will be free. And the order there is not arbitrary. If you have one binary and one continuous, it's always better to fix the binary one. And then we fix the variance of this. So the only free parameter here will be the loading of the positive part. And that will correspond to then the covariance between these residuals. And the model for the 2-part is the same, but we don't have to add this factor because, as Bengt said, this doesn't come into the likelihood, so we don't have to bother about it. But then in the analysis command of the Heckman model, there is some technical things. We use the probit link in both cases, but then we have the M convergence option here. And this is because the likelihood is very flat in this case. So this just increases the precision in the numerical precision. So this is how close does the numerical derivative has to be to 0 for the algorithm to converge. And I just wanted to say, and we have the number of integration points here, and I just wanted to say that the defaults in Mplus are really good. So if you feel uncomfortable working with details like this, then you should just trust the defaults and have the same analysis as you have down here. You can just skip this, but this is an option for people that are more advanced users, and also if you want to see how these things affect something. If you want to do a simulation study, for example, you can shift these things. And there's a good paper on the number of integration points that I will refer to several times, because I think that we will not have time to go into and explain these details, but it's good to read up about it. OK, so now we're going to look at and compare these models. And actually, we cannot compare all 4 because they're on different scales, right? Because the sample selection model and the 2-part model, as we specify them now, use the log of y for the positive part, whereas these use the original y. So we cannot really compare these two. So we have to compare the censored normal versus the censored inflated first, and then the sample selection versus the 2-part. We will look at one crude way to actually compare even all 4 of these models in a couple of slides. But for now, we can just compare these two. And we can see here that the censored inflated model have a lower BIC. So even though it has almost double the number of parameters, it has better fit because the BIC is smaller. And when it comes to the 2-part versus the sample selection model, the 2-part model is somewhat better. It has 1 parameter less, and it has better BIC here. I will talk a little bit more about these outputs. All right, so let's look at some outputs from this. Let's start with the censored normal model. We have 4 models now that we looked at. So let's start by looking at the output from the censored normal, the Tobit regression. And let's look at the effect of being Hispanic. So being Hispanic here has a negative effect. So you're drinking less on average if you're an Hispanic person, given that everything is the same. It's a significant variable. But as we could see, the inflated model had a better fit, right? So if we look at the inflated model instead, we have the same kind of regression here, but then we also add the inflation regression equation here. And now we can see something else. We actually see that being Hispanic is not longer a significant covariate for the amount of drinking. So it's a negative effect, but it's not significant. So there's no effect. Whereas for the choice, if you can call it a choice, of being a never drinker or a drinker, it has a significant positive effect. So in this case, Hispanic individuals are less likely to be drinkers than the non-Hispanic individuals, or I guess white Caucasian is the baseline here. But if a Hispanic person is a drinker, then the fact that this person is Hispanic doesn't affect how much this individual drink on average. So again, we see the kind of the new information that we gain from having this inflation equation, the utility of that. All right, so like we saw here in the model fit measures, the Heckman and the two-part model was very similar. And actually, the Heckman residual correlation is significant in the Heckman model. So it's difficult to choose between them. The BIC might suggest that we're going to go with the two-part, but also the correlation was significant, so that might tell us to go in the Heckman direction. And of course, this should be a choice of substantive reasoning, right? We should think about what makes sense. If it is a missing value, like the Heckman model suggests, or if it is an absurd value, like the two-part model suggests. And I really recommend the papers by Duan there, because I think they're really good explanations of how to think about these things. And if we want to compare then the censored inflated versus the two-part, they have similar results. One thing that you will see if you look at this is that the signs are flipped for being at 0 or not. And that's reasonable because in the inflation model, we model the probability of being in the 0 class. But in the two-part, in the Heckman model, we model the probability of being larger than 0. So we should have flipped signs if the models agree. Like we said before, the log likelihood and the BIC is not really comparable. So what we can do if we really want to compare a two-part model to a censored inflated model is to calculate the probability of some specific value for some specific group. So in this case, we can calculate the estimated probability of 0 heavy drinking and the mean of heavy drinking for a subset of males who have 0 values on the covariates Black, Hispanic, early onset of heavy drinking, family history of drinking, and high school dropout. We can compare that to the sample values for these. So the sample probability or the sample proportion of 0 drinking is 0.44, and the mean of heavy drinking is 1.538. And then we can look at what the two different models predict for this specific case. And we can see that the censored inflated model and the two-part model have very similar probability estimates for being for being in the 0 class here. Now we flipped the sign, so I've corrected for that. But the mean differs here. So this might suggest that the censored inflated model fits the data a little bit better than the two-part model. But of course, this is a very specific case. This is not an overall fit measure. This is a fit measure for just this kind of point in the parameter space. But you could, of course, add more and look at a lot of different combinations and different subsets if you think that it's important to compare between these two models. So this is one way to kind of evaluate the fit, even though they are on different scales. And just to round up, I'm going to look at this variable again. And as an assignment here, you could think about having an ordinal approach. So you could keep treating this as a two-part model. You can think about it as being at 0 or not. But then you could think about modeling this part as an ordinal variable, which kind of Bengt hinted at in the beginning. It doesn't really look continuous. And actually, it makes sense as an ordinal variable because we know that they're order categories, right? They are combinations of how many times you have engaged in heavy drinking. And there's not too many of them. If you have a two-part here, then there's only 1, 2, 3, 4, 5, 6 categories. So it kind of would make sense. So how would you do this? Well, you would specify that the positive part of the two-part variable is an ordinal or a categorical variable. But then you would not like the logarithm transformation anymore, right? Because now we're going to view it as an ordinal variable, so you don't want to take the logarithm of the positive part. And here comes in then overriding this default of taking the logarithm of the positive part, which is easily done in the data two-part command. You simply say transform equals none. And this would also apply then to if actually this part did look like a normal distribution to begin with, and you don't want to use the logarithm transformation. If it is already a normal distribution, then you don't have to bother. So this is how you do that. So you can try that out. And you can see now that we have a lot of combinations that we can try to work with these piles or inflations of zeros. And with that, I think we have reached the break.
Yeah, except for the question and answers, yeah.
Yeah.
So there you have it. That's an assignment for you, but we're not going to check them. But that's a hot model, that last model. You don't often see zero-inflated ordinal regression. I think maybe Don Hedeker has dabbled in that area, but it's not often used. And I wonder, maybe it's a good model to work with in many cases. Anyway, you've been very good hanging in there long morning, right? But nobody yawned, so it looks pretty good. And this puts us in a very good position for the rest of the day. So what we want to do is just take a little bit of question and answers before you get your 15-minute coffee break out there. So let's see, who has the first question and who can be very down to earth and ask a very simple question, you know, some misunderstanding on the first slide or something like that. Yes, lady in the back. I guess we have microphones here somewhere. Maybe we can pass them around.
Can you hear me okay if I talk like this?
Yes.
Okay.
All right.
So in the comparison of results slide, it says the Hopkins residual correlation is significant. Did we show that anywhere?
If we show that in the output, you mean?
Is it in the slide?
No, it's not in the slides. No, I agree. That's kind of a jump there. No, that's why I would say I'll come back to that result, because we didn't really look at the outputs. There's so many combinations here, so we didn't really have time to look at all of them. But it was significant, and that might suggest that it's a fit.
Gentleman in the front here.
So, I'm thinking in slide 30, if I wanted to output the model estimated values from a Poisson or negative binomial or anything else to make this plot in other software, is that available in the save data command?
Well, you know what? We're fortunate here to have the key programmer of Mplus in the audience. Except, yeah. Yeah, so everything that's plotted, the information can be saved and taken to another software like R for doing pretty plots. Yeah. Gentlemen.
Yeah.
The values are in the residual output, the output option residual. Yeah, okay. Gentleman in red.
My data is multi-level data. Is it okay to log any kind of multi-level modeling with this kind of Poisson, zero planar one, and binomial one?
So the question is, if you didn't hear it, multi-level modeling, can we do all of this modeling in that case as well? And yeah, you can do count modeling in the multi-level settings. And I see no reason why you can't do sensor. What do you say, Timur?
No, yeah, all these are available.
Yeah.
For two-level models.
Right. So, by the way, Timur here, he's carrying our senior statistician and star statistical programmer and co-author of many papers showing the statistical underpinnings of Mplus. He actually walks around with his laptop and has the Mplus code on it. And for a small fee, he'll show it for you. All right, yes?
As we move towards looking at mediation, would you ever use this where your zero count is those in the treatment, in a control group, plus the few in a treatment group who didn't get some sort of a intervention?
Yeah, that's dealt with a little bit in the non-compliance modeling, which is a mixture model, and you have examples of that in the user's guide. So it's so-called case modeling, complier, average causal effect modeling, CACE. And we have a special page on the website called Randomized Trials, where we have most of the papers that we wrote some 10, 15 years ago on non-compliance modeling. So you can actually then compare treatment effects between control group people and the compliers in the treatment group. So that leads to mixture modeling. But we're not really covering that today. We only sort of slip into mixture modeling. Mixture modeling is not the focus of today, but we use the mixture modeling for the inflation part. All right, more questions? Yes?
So slide 27, random intercept Poisson.
Slide 27, okay.
So we have F by N affairs. So in Mplus, that means N affairs at the rate of 1 is default, right?
That means what?
The loading is,
Its loading is 1 by default in Mplus.
yeah.
Right.
So what is the useful information? So the variance of F is equal to the residual variance here?
Yeah, exactly. So the question is, this loading is fixed to 1 by default. So what's the use of doing this? Well, you have the variance of F, and if you go back to the slide for the formula.
Do you know where it is?
Yeah, it's the one more there.
Oh, sorry.
This one. So this is F. And you get the variance of that epsilon.
Yeah, so it's kind of adding a residual to the
So that's
Poisson
just a
model.
little trick. since we, yeah, I'll stop there. All right, yes, lady in the middle.
For the inflated models for count data, the inflation part is modeling the probability of, like, for instance, with our example where it's modeling the probability of being zero, so like no affair.
So the question I think was,
No, go ahead.
as we discussed over breakfast this morning.
Yeah, we actually did. That's-
Yeah. So the question was about the inflation model, I think, for counts, and what is that inflation part of the model? Is it modeling the probability of being zero, the observed zero? And the answer is
No. We're modeling the latent class here. So being in the class of 0 where you are actually a never drinker rather than a drinker that didn't drink this time. So you're modeling the probability of being in one latent class here rather than the actual observed 0. So that's how it differs from the two-part, really.
And I guess, just as a follow-up, what is the rationale for the difference between how the inflated part is modeled between the, say, the zero-inflated negative binomial models and the two-part model?
Well, I guess you have to think about if the 0 can be two things. I mean, if the 0, like for us, in this case with the heavy drinking, it's a good example of where it could be inflated in the sense that you could have a 0 that means that you're never drinking ever, or you could be just this, as I said, a drinker that didn't drink this time. But in other situations, the 0 might always be only one thing, so to speak. It's not part of the outcome. It's just if you're not engaging in the behavior or not. So the 0 is not meaningful for the continuous scale. Maybe is one way to think about it.
so if you have an inflation model, you can always estimate the probability of being in the 0 class. And then you have the observed probability or observed proportion in this answering 0. So observed proportion answering 0 minus the predicted probability of being in the 0 class is the probability of having the observed 0 based on the regular Poisson or the regular censored Tobit. So you can compute those and see what the portions are contributing to that probability of being at 0. All right. Yes.
So sort of related to this, what can you do differently, or I guess better, if you actually know who is in the 0 class?
If you know who is in the 0,
If you know who are non-drinkers.
then we have a feature called training data for mixture modeling. That is, you can say this person we know for sure is in a certain class, whereas some others we don't know. We want them to be put into the 0 class. So there are examples in the user's guide of that too. If you look in the index of the user's guide, under training data, you'll see how to operate that.
You could also do multinomial regression, I guess, if you think about them as 3 different or 2 different groups.
Yeah, but then you want to have ordinal for the.
Yeah. Okay. True.
But so how come you know this?
Well, we actually do alcohol research, and so we actually know who are drinkers, who are non-drinkers, but then you do have the case of people who just happen not to drink
Yeah.
over the last
Okay.
week. So,
Yeah. Sounds like training data. You have a mixture expert right in front of you. Actually, I'm sort of calling out names here. So they're going to help me in the break when you want to ask questions. Catherine Mason here, mixture expert, teaching about it at Stats Camp very soon, I think. Right. All right. More questions, or do you want to go out and have coffee?
One quick one.
Final question then.
Real quick, because I got a little confused with the last few questions. Now can we talk about the inflated model relative to the Hispanic example one more time? Show the difference in the inflated.
So the question is about the censored modeling inflated. And all right.
Do we have a good slide comparing them somehow?
Do you have a particular slide that you're interested in?
absolutely.
The one with the big question mark on.
48.
Yep, that's exactly what happened.
You can take a little bit more time, so I had to order more coffee from upstairs. And they're brewing it fresh, so it's going to take about 10 minutes.
Worth waiting for.
How many minutes should we drag this out?
Okay. So,
5 minutes.
All right. I think
right, so now
they look like they can handle it. They're very perky.
yeah. Okay. Okay. Repeat the question now when they have the slide.
If you just explain it one more time, the Hispanic and this, I think you included it. Before we're talking about counting, it's different.
Yeah. Yeah. So on this slide, we can see that Hispanic has a non-significant effect on the count value. But it has a significant effect on whether or not you're in the latent class of a never drinker or not. Now you have to think about if this is the drinking data. It is the drinking data, right?
Yeah.
This is flipping between data set. So it has a significant effect on whether or not you're in the class of people that never drinks or the drink. So on average, Hispanic people apparently have a higher probability of being never drinkers than other people in this case. But if they are drinkers, they do not drink more or less on average than the baseline group in this case.
And of course, all of this is a lot of information, right? So that's why it's useful that we have the book where you can read about this in more detail. Yeah. One more question here.
So if you go to the next slide, based on that table, okay, you said that the sense of inflated estimate is better than the two-part. Can you tell me how you reached that conclusion?
Yeah. Yeah, for sure. Yeah, I guess that's a.
So the question was, for those in the back, how did Morten reach the conclusion that the censored inflated was better than two-part at the bottom table there?
And first of all, I want to say that that's not clear. This is just a very small way, very crude way of looking at comparing these models. But in that comparison, it's better. And how I see that is that we essentially want to evaluate the fit of the model's predicted values to what we see in the sample, right? Just like with the plots before, we have what we see in the sample and the predicted probabilities. So here we have the predicted probabilities from the censored inflated model. So this is the predicted probability of being in the never drinking class from both models. And then we have the mean of the variable heavy drinking. And then this is the sample values. So this is what the data says if we just look at the data without any model. So what we want is the model to be close to what we see in the data set. So the censored inflated, they are similar in this measure. So both are about 4% off when it comes to the probability. But you can see that the censored inflated is closer to 0.53 than the two-part estimate when it comes to the mean. But again, this is just for this very specific subgroup where we compare the probability of only one outcome, 0 in this case. Of course, as I said, you can look at several if you're really interested in comparing these two models. But we cannot compare the BIC between these two models, right, Bengt?
Right. So two-part has the log. So the question is, can we compare those models at the bottom with BIC? And the answer is no, because we do the log transformation in the two-part analysis, but not in the censored inflated analysis. So when the when the dependent variable is on different scale, BIC ends up in different metrics.
Yeah.
So they're not comparable.
Yeah. The likelihood part is different, right?
Yeah.
There is a transformation that can make them comparable.
Yeah. And Tiamer will give that transformation to you.
Instead of coffee.
Yeah. There was one more hand up here. Yes.
Yeah, so regarding the BIC comparisons, I'm thinking, and I hope this makes sense and isn't really misguided. When we do things like chi-square comparisons, we test the significance of the difference between fit indices. I guess the idea there is that we need a relatively substantial difference in fit to justify retaining a less parsimonious model, or retaining a more parsimonious model. So it doesn't seem like there are guidelines for how to compare the BICs in terms of is it a substantial difference? Are there recommendations about that?
There has been some writing on that. I think we have a FAQ, frequently asked question item or bullet on our website on that. Wasserman and others, I can't remember exactly. But there's some thinking about what should be considered strong, medium, or weak evidence. But I don't know how dependable that is.
No, it's kind of a rule of thumb part of statistics, which is difficult. So you always have to that's why I always stress that you want to think about if the model makes sense in a substantive point of view, from a theoretical point of view.
But you may want to take a look at that fact.
Yeah.
Okay, because the BIC, the metric would vary. So there would be some, I suppose you would need to contextualize the metric in order to have a rule of thumb. Is that correct?
But if they're on the same metric, then there is kind of a rule. There are some suggestions in those papers.
Yeah.
And then there are the transformations that Theorem talked about where you can actually translate to the same, I guess. But
right, I mean, within
Yeah,
Yeah.
that's impossible,
Yeah.
pretty much,
Right.
I would think.
Okay, thank you. Well, one more question. How can we apply some of these models into the factor models?
So the question is, can we apply these models in factor models? And that's exactly, yes, why we want to teach this, because everything we say about regression analysis translates to factor models. So you can have these dependent variables can be your factor indicators. So we're teaching you something very generalizable. So there was somebody else, yes?
Slide 33.
Slide 33.
Model fit. The hurdle model is translated into binomial or almost identical model fit. Is that common because the way the models are calculated, or is that just maybe a synthesis of data?
Wait, could you say that again? Somebody was...
The zero inflated negative binomial and the two-part hurdle model, the model fit is almost identical.
Yeah.
Is that common because of the way the models are calculated, or is it just maybe a synthesis of the data?
You know, I don't know how common that is. I would think it's data related in this case. I don't think it's very generalizable. But then I haven't studied enough
But I
data
guess
sets to be able to say.
I guess that has to do with how the zeros are made up. If there's only a few zeros that are actually never drinkers, if you think about it in that example term, then the two-part and the inflation part would be similar, I guess.
Perhaps, yeah.
Yeah.
There is one of the things that in these models to consider is that whether the two-part consists of, I think that the two-part hurdle models, the zeros are independent, right?
Yeah.
The model where the zero inflated negative binomial gives you a combination, so you have two sources of zeros. So that it's actually quite different. The model should be not general.
No, that's true.
Okay.
So there are two sources of zero. One thing from the negative binomial and then from the inflation.
Right. Yeah, right. So for zero inflated negative binomial is, really taking two approaches to fitting the zeros very well. So I would think almost overfitting in most cases. I think if you use a negative binomial, I would think that most often, but I may be wrong, most often you don't need the inflation part on top of that. But you can use it.